Hello everyone, it's October 28th. Alright, let's do this. Maximum, it's always grid these days. Maximum number of moves in a grid. Max number of moves in a grid. You're given a zero indexed matrix consisting of positive integers. You can start at any cell in the first column of the matrix and traverse the grid in the following way. From a cell, you can move to any of the cells, row -1, column +1. Wait, row -1, column +1, so diagonal to the top right. Row, column +1, row +1, column +1. So you can move here. You can move this way, or this way. Yeah, no. Diagonal. Right? That's the three ways you can move. Such that the value of the cell you move to should be strictly bigger than the value of the current cell. Return the max number of moves that you can perform. Okay. So you cannot go down. You can only go this way. All right. It seems like it seems to be a DP problem, right? For example, we can say that I'm using the first one as example. 1, 2, 3. 1, 2, 3. So we can say the maximum to move like starting from here. If we go from bottom to the top, right? So start from this one. Maximum to move for this is 1. And actually, no, I don't think that's 1 because this, how many is this? 1, 2, 3. That's 3 moves. So this is always 0 because I cannot go up. I can only go this. So this is always 0 move. This, right? Can I go this? Can I go this? Actually, this is the one we should do because I cannot. So all of these are 0 because I cannot go down. I can only go this. So these are 0, right? Next, we can go this one. Can I go this way? No. Can I go this way? Yeah, so this is 1. And this, I can go this. I can go this. So this is also 1 because I can go this, this, right? And this, I can go this way. So this is also 1. This is 0. This I can go this is also 1. Yeah, so basically from here, the maximum I can go is 1. Now from this, I can go, this is 1. And I already 1, so this is actually 2, right? So the maximum step to go is 2 because I got 1, 2. Here I have 2 as well. And here I have 2 as well. And this one I have 2 as well. Here I have nothing. This is a 0 because there's nowhere I can go. Right? Because from here I cannot go to the 0. And this I can go. So basically you have to pick the largest among these 3. Right? Largest among these 3. If it can go largest among these, and then this will be 3. This will be 0 because I can go none of them. This I can go 3. So the answer is, when we reach the top, to find the biggest answer. Okay, yeah, it's a not very complicated DP problem. We shall be able to do it. All right, so what we can do is we can do it in place. Ooh, I don't think we can do it in place. Nope. I don't think we can do it in place, which is fine. We'll do it not in place then. We can say dp okay, and for int I equal to m minus 1, I larger than 0, I minus minus, we say dp what is that, dp I n minus 1 equals to 0. Oh, I don't have to do it because they're already 0. Damn. Basically, we set this to 0, so we start from this one. Okay. We start. Actually, it doesn't matter which one you start because we check. What we checking is here. I think I have a better idea. If we make it slightly bigger. Yeah, if we make it slightly bigger, like 2 more rows, then we can do it even better. I don't know. No, I don't like it. I still like how we're doing right now. Okay, so we're gonna say int I is equal to m minus 1, I larger equal to 0. Actually, no, I think I shall go j first. N minus 2, j larger equal to 0, j minus minus, and then we have I, right? I is this, and I minus minus. Okay, so for each one, we will check 3, right? We check 3, and if so if it's larger than, then we take 1 plus this. If it's smaller than that, we take a 0. Yeah. Okie dokie. We can say k minus 1, k smaller equal to 1, k plus plus. Okay. If I plus k is larger equal to 0 and I plus k is smaller than m, okay, and grid ij is smaller than grid I plus k, j plus 1, then dpij shall equal to math.maximum dpij and 1 plus dpi plus k, j plus 1. Okay. Once we're done, int res equal to 0. I mean, we can just do it along the way, right? And eventually, when we're done, we say res equal to math.maximum res and dp. Oh, I just realized something. Yeah, we'll do it later. We can do it simpler. dp 0, right, first row, and then j. All right, I think we can do it. We can get away with 1. Yeah, we just say equal to dp that. Yeah, we can get away with it. We just need 2. Okay, so let's redo this. Int dp m, okay, int temp temp I is maximum dpi plus dp. Nope, this is temp 1 plus dp I plus k, and at the end, yep, it's dp 0 and dp equal to temp, and at the end we'll return rest. Two, 6, 8, 4, 8, 4. Use dp from bottom right to top left. Each dpij represents the max number of moves starting from grid ij. In the actual implementation, you can use 1d-dp. Let's see if we write it right. Interesting. That is now good. All right, let's see what was wrong. dp is this, that's fine, and -1 and -2, that's fine, and I equal to m minus 1, that's fine, and then we go 1 by 1, and then k is going to be I, right, -1, 0, and 1, -1, 0, and 1, right? Okay, and then we say I plus k is larger equal to 0. Yes. And smaller than m, yes. And then grid ij, which is this one, is smaller than grid I plus k. And then j plus 1, yes. And then we say temp I shall equal to maximum temp I, and then 1 plus dp I plus k. And if not, it's just going to be 0. Looks... Oh, I think this probably should be temp. Okay, got one right, and this one. Huh? You cannot perform this move?
Is it recycling?
Yes. Hold a second. You can start any cell in the first. Oh, in the first column. My God. I got it wrong. Damn, in the first column. Ugh. Sorry, I was not thinking. That was the first column. Which means once we're done, we just need to find the largest of the DP. Alright, we'll just do the largest of the DP then. Oh, we got it. Yeah, that's pretty bad. And we say res equal to mass dot maximum res of v, and then return res. There you go. That was a little bit oversight. Pretty straightforward, this problem. Yeah, I guess didn't read the question carefully, so issue was on me. Yep, top down, bottom up, and then bottom up. Space optimized bottom up. I think they're using the same method. Oh no way. Oh, it's doing. Wait, hold a second. How is this space optimized? Oh, I use this technique. Huh. I wonder. Okay. Now that's that. Alright, let's take a look at this one. We used some technique to do this with, I remember, with a lot of optimization. Now we got it done. I think we traverse it. We find the depth, the height of each position, and then we find which nodes belong to the impacting, right? And for the one that's not impacting, we return the result. For the one that is impacting, what we do is, for the ones that is impacting, we simply start from there and we traverse back up. Right, we'll traverse back up and update the height, update the height, update the height. Okay, so that's what we did. Let's see, what's the hint on this one? Pre-compute the answer for each node from 1 to n and answer each query in O1. Okay. Pre-compute the answer for each node. Oh. Oh. You're kidding. Oh. Pre-compute. Oh my God. That is true. I didn't think of it. We just pre-compute this result. Damn. Yeah, we go through the whole thing. We find their heights, right? And then we go through them one more time. Right, we go through them one more time, and each time we go through, well, ignore the first one, From the second one, we can say, okay, if I remove this, but I have the first one, so I can check the other side and then get the height. And then we okay, it's not as straightforward. And still need to think about it. Because at each node we say, okay, we delete you, right? And then we know the impact, and I have the other side, so I know, okay, so you cannot use this side, you have to use the other side. So if the side that's removed is a smaller, then there's no impact. If the side that uses the bigger one, then we have to go for the other side. But how do we... Well, you have to pass down the height from the other subtree. Right, so from the start you have the left tree and the right tree, and in fact you got the left tree. If it's smaller, then yeah, it's always going to be smaller. You will return the yes, and then you pass the right as well, and then each one it's not gonna matter. It's not gonna matter. All right. So yeah, we go from the top down, and if it's non-impacting, if the subtree is non-impacting, then every one of them will be non-impacting. If it's impacting, which means if you go down the path which is bigger, right, and then you say I remove this, then the result will be, the other side plus 1, right? So you remove this, will become this. Remove this, will become this, okay? And then if it's the larger one, the impacting one, will go down, and you say it's impacting. And you also pass down the other side. Actually, do you even pass down the other side? Because you know as you go down, if you want to remove this, you have your other side. Okay, so you want to remove this. Other side is bigger, so it's non-impacting. And if it's non-impacting, everybody in your subtree is non-impacting. If it is impacting, right? If this is impacting, how do I know the height? Well, you know the height because originally it's the other side, right? And the other side is impacting. The other side is impacting. So if the other side is impacting and then your side is not impacting, and when the other side gets removed, then you know the difference in your height, right? So you know the difference in your height, then you know how much. Yeah, is that true? If it's impacting, that's actually not true, because it's not just based on your other side, it's based on, yeah, how do we do this in one go? How do we do this in one go? Right, we know this is impacting. This is not impacting because this is 0, 1. This height is 2, right? And then this is 0, 1, 0, and this is 2. Oh, this is 3. My bad. It's their height, right? So you go down. Huh. You go on this path, you know that this is not impacting because it's bigger, so this result will be 3, and this result will be 3, right? So you go down this path, okay, we remove this, then you know it's gonna be bad, and because this one's bigger than this, bigger for 1, then you say, because that's on the second level, so you say the answer will be 2. So you can do this as 2, which means when this one gets removed, right? When this one gets removed, the total will be 2. Okay. Now we're coming down to this. This is smaller than this, so this is going to be 3 because it's non-impacting. Now, for this one, 1, if I remove this, what's going to happen? Well, we look at the parent, right? We look at the parent, and it's the parent. If the parent gets removed, it's going to be 2. If the parent does not get removed, you get 3. Right? Parents do not get removed, you get 3. And you are the one that's contributing to this. So if you got removed because you are bigger than this, so if you got removed, then you know the parent become 2. Right? If the parent become 2. And can we say something like this? Because if the parent gets removed, you will rely on like something else, right? So if a parent gets removed, rely on something else, you get a height. And if parents do not get removed, right? Do not get removed, and the parent has a height. If the parent do not get removed, then we have a height of, another value, right? And which means without the parent on the other end, the maximum height is this value. And now with the parent, right? But with the parent contributing 1 less. Because with parent, parent height is whatever, and the total height can be a certain value, right? So with the parent and without the parent, it is smaller. Then with the parent, but with the parent contribution reduced by, reduced actually need to be by 2. That's not true. That's not true. Because you have the other side, right? You have the other side. It's because of you, it gets this. Now the other side can still provide. So you can check the other side to decide, okay, now the parent's going to be this height. So the contribution from parents reduced by a certain amount, right? Reduced by a certain amount, okay? Which means if we still follow the parent, then the height will be whatever the previous height minus this amount, okay? Minus this amount. And I compare that to if parents get removed, which means the other side, how much that is, the maximum that is. And based on those 2 values, we can decide, okay, what's going to happen. That seems complicated. That seems very complicated. But it might work. Okay, let me just go one more time. So after we get the height, right? After we get the height of each, then what's the point of having the height of each value? We need a height of each value to compare, right? So now starting from the top, now we have 2 neighbors, left and right. Then we compare the 2. If one side is smaller, then that side will be designated as the non-impacting side, okay? And if it's non-impacting, everybody in that subtree will become, just, you don't have to deal with this. Now if the 2 are equal, then they are both considered non-impacting, and then we just, so it's only when something is bigger then you have to be worried, okay? Then you have to be worried. Okay, so one side is bigger. So when it's bigger, so you need to consider, what will happen if I remove it, right? And if you remove it, right, if you remove it, then you need to know your sibling. Okay, how much is sibling? So based on the sibling, you can know your parent. Right? Based on the sibling, you can know if you remove it, the parent's new height. So you get a parent's new height. Okay, that's good. And then you need to know if you remove the parent, what is the height? And you remove the parents, you get a height. And then with your new height, with your parents' new height, and then with your parents, you know the height, right? Now without you, the parent gets a new height, so you know the reduction, right? You know the reduction, so you do the reduction on that, and then you compare to, yeah, that might work. That might actually work. But we'll leave this tomorrow. I think it might work. And I can run like 2 rounds.